So here we go. So then you get, when you do that, don't try to copy this down. Just listen, compare it to what you did, look at the video later. So you get 4 minus 4 over u, essentially, is what you get. 4 minus 4 over u. And then your antiderivative is 4u minus 4 ln u. Okay? And so then we substitute back in 4x plus 1 minus 4 ln x plus 1. Okay, and then so then, now that I'm substituted back in for x, don't keep your limit as infinity. You have, you have to change to a limit problem. Okay, so I tried to show that on Wednesday, but I saw lots of you. You're putting the limit, you're putting infinity in one of these limits, and then you're thinking about plugging in infinity. You can't plug in infinity, right? It's not a number, but you can look at the limit as a number gets really, really big. That's what we need to do. So we change the infinity to a, or some other symbol, and we look at the limit as a approaches infinity. So I plugged in my a, I plugged in 0, and then when I take the limit, I get this. I get 4a minus 4 ln of a plus 1 is what you get in the end. Well, the limit really is kind of like really, really big minus really, really big. So this is what's called an indeterminate form. Other indeterminate forms are like 0 over 0, infinity over infinity. So an indeterminate form means that it could be a constant value. It could be 0. It could be infinity. It depends on the situation. It depends on what you in particular have. So we don't have time to do this limit, but this particular indeterminate form diverges because we're comparing a linear to natural log. And so a linear will get infinitely bigger than a natural log. That's what we're saying. We'll take a linear function minus a natural log function. The linear function will just keep getting larger and larger compared to a natural log. So this particular infinity minus infinity is infinity, okay? So this is divergent, which agrees with what we said, right? It agrees with what we said about the accumulation, that at that rate that levels off at 4, your accumulation is just going to keep growing and growing. Questions on page 1? Okay, page 2. So the gist here is that you have the 2 over x squared is going to decrease rapidly. And the 2 over radical x is going to go to 0. That limit will be 0 as x gets large, but it will get there a lot more slowly. And if you remember that what we said from last time, we talked about integral of 1 over x to the p. Or so say a. Okay? We said last time that if p is greater than 1, like R1, it'll converge. It'll converge to, your accumulation will converge. If your p is less than or equal to 1, like this one, which is like the one that decreases to 0 more slowly, the rate more slowly, that will diverge, right? Because it is going to 0, but it's too large. It goes to 0 too slowly, and the accumulation still gets really, really big. It doesn't level off. Okay? So what is the necessary condition where you would say that my improper integral may or may not converge? What has to happen so that we even can have a conversation about the accumulation or the integral converging? What has to happen with the rate function?
The rate function has to approach 0.
Yeah, it should make sense. The rate function has to approach 0. If the rate doesn't go to 0, if it goes to something else, what's going to happen to the accumulation? It's just going to keep growing and growing and growing, right? Just like that for page 1. So if the rate function gets really, really small, goes to 0, then there's a chance that it will. Is everyone paying attention? This is really important. If the rate function goes to 0, that doesn't guarantee that, just like with this example, it doesn't guarantee that your accumulation is going to level off. You still can have rate functions that go to 0 but goes too slowly, and the accumulation will just take off. So the rate needs to go to 0, but that's not enough. It also needs to go to 0, what? In a certain way, quickly enough, right? It needs to get to 0 quickly enough, and then your accumulation can level off. That's the answer to question 3. Yeah.
Quickly, if the rate is some sort of variable rate, like a sine function or something like that, it would also.
Right. So yeah, your rate of change has to approach 0. Anything else, and your accumulation can't possibly converge. So only rate of change functions that get really close to 0 have a chance that their accumulation will converge, the integral. Okay? And so then which ones do? The ones that get to 0 fast enough. If it doesn't get to 0 fast enough, it will still diverge. Does that make sense? So that's the discussion of number 3 down there. So talk that over amongst yourselves when you study, okay? Make sure that you understand what I'm getting at with this 2-page worksheet. There's kind of an overall theme to this worksheet, understanding when these improper integrals, when they diverge and when they converge. Okay, so shoot. I wanted to work through this example. But it's too long for 4 minutes. It's more like 10 minutes. So what I can do is I'll just keep running the video and I'll just do it. And if you need to go, if you need to slip out, if you do so quietly, I appreciate that. And then I'll just finish the example. When I finish, I finish. And if you need to leave, then you'll just pick it up with a video. Okay. So I was talking about this one. And so we're looking at, we got this rate function, 3x e to the 0.5x. And we're asking about the accumulation at this rate. It's kind of backwards though. It's like starting at negative infinity up to negative 2. So we're talking about the accumulation due to, so if I just graph, say, x less than negative 2. So is this a worthwhile question, or can we just say, no, it's going to diverge? That integral will diverge. Or is it a worthwhile question? It's a worthwhile question. Why? Well, we don't know how fast it is. It just doesn't approach 0. That's the question.
Yeah,
0 in the negative direction.
Yeah, that's okay. Not in the positive, in the negative direction. So if this thing didn't approach 0 as x went to negative infinity, then we would just say, game over. It can't possibly, the integral or the accumulation can't possibly converge. The only possible way it could converge is if as x gets large, in this case large negative, the rate goes to 0. Does that happen? Most certainly, right? Most certainly. Okay, so then we say, how do we know if it converges or not? So we've got the necessary condition. The rate goes to 0. How do we know if it converges or not? Well, it's not of the form 1 over x to the p. So there's only one other way to find out. We got to do it, right? We got to do the math. We got to just evaluate this. And when we take the limit, if we get a finite value in the end, then we can say this is a convergent integral. And if it diverges, then it diverges. I'm sorry, if the limit diverges, then the integral diverges. Okay, so here we go. How do we do the antiderivative of 3x? So we're going to start by doing the limit. Say as a goes to negative infinity of a to 2, negative 2. 3x e to the 1/2 x. This is a job for undo. You should notice this is undoing the product rule, right? If this were x squared, then it'd be undoing chain rule. But it's one of our common forms for undoing product. A power of x times e to the something. That's undoing product. Okay, so what do we got? We're going to do f equals 3x, f prime equals 3, g equals e to the 1/2 x, g prime g prime equals e to the 1/2 x, g equals 2e to the 1/2 x. I'm afraid there's another class in here after us, though. Okay, good so far? So we have the limit as a goes to infinity of what? F times g minus integral g f prime g. So let's just set this up. I think there's a class in here, so I'm going to have to just finish the video myself and post it, and you're going to watch it. But here's the step. F times g would be 3x times 2e to the 1/2 x minus integral 3 times 2e to the 1/2 x. Did I do it right? And now, so now we've got to do that antiderivative, which is easy, and then we got to evaluate the limit, and I will post that as a video. Okay.